Hello and welcome to another video, this time taking you through the MAT 2014 question 3. Um, Quite like this question, it's not easy, but yeah, which bit is it? This bit is probably the toughest, and a bit at the end is a little bit of a pain as well sometimes, but it's mainly this bit. Um, but yeah, it's nice though, it is nice. It's obviously describing the exponential function, and that's why it's said straight away at the start, forget the exponential function, even though we're describing it. It's almost like they're trying to, show you how you can derive the exponential function, just assuming these three properties, like the exponential function follows that. That's what f of x is going to be according to these three, constraints. But anyway, let's have a go at it. So we're told that f of x plus y is f of x, f of y. Df of x, df by dx equals f of x. They're saying f differentiates to itself there, and f of x is greater than 0. So it certainly sounds like they're describing the exponential function, because e to the x times e to the y equals e to the x plus y. E to the x differentiates to itself, and it's always bigger than 0. Like, you can see why they've banned that. Anyway, forget the exponential function, because we're not allowed to even know about it for this question. It's a cool question, it really is. Okay, so let a equal f of 1. Show f of 0 equals 1. Okay, so I'm thinking what I need to do essentially is pick 0 plus 1 in here, because then I've got f of 0 times f of 1, and obviously f of 0 plus 1 is just a. F of 0 is what I'm looking for, and f of 1 is a, and dividing by a gives f of 0 equals 1. It's a lovely little question. They're just training you on the formula here, on the conditions that they're giving you. Now, let's try part 2. Part 2 is not too bad either. Integrate f of x. Now, we've already said from property B, it differentiates to itself, so it's also going to integrate to itself, because you could, well, if you like, you could integrate both sides of this equation, actually, interestingly enough, giving you f equals the integral of f of x dx. That's exactly what would happen if you integrate both sides of that equation. But yeah, so clearly the integral is going to integrate to itself, and so it's going to integrate to f of x between 1 and 0. And that's f of 1 minus f of 0, which we've just deduced, or been told. F of 1 is a, f of 0 we deduced was 1. So that's a minus 1. Oh, we showed it. I didn't even look at that. So there we go. The trapezium rule with n steps is used to produce an estimate for in for the integral I. Show that in equals 1 over 2n, b plus 1, b minus 1, a minus 1. This is painful. This is a bit more painful. You've definitely got to realize a few things. First thing I did when I was doing this was I drew a diagram, because I want to see what's happening with the trapezium rule here. Now, I did kind of cheat a little bit in my head here, because I did think, well, they told me not to assume, you won't get any use awarded any marks for use of the exponential function. But I mean, I know it is the exponential function, so I'm going to draw it as the exponential function. But the diagram doesn't really matter anyway, but it just gave me a better feel for the problem. And I dotted a line down here. Now they're interested in the integral from 0 to 1 here. In is an estimate for I, remember, so we're going to draw this from 0 to 1. And I just sort of like cut up little bits here, and I realised, well, if we've got n steps, this is going to be a gap of 1 over n as we're going from between 0 and 1, obviously. 1 over n, 1 over n, 1 over n, 1 over n. That's what's going to happen. And so if you're doing the trapezium rule with that, you're going to need the trapezium rule formula, which is in is going to equal, okay, strip width over 2. Well, that's half of 1 over n, which is 1 over 2m. Ends plus 2 times middles. I'll just write that for the moment, just so you remember what I mean. It's I think, quite a typical way of remembering the trapezium rule. It's a nice little shortening of what is otherwise a, unwieldy looking formula. The ends are obviously the y coordinates, so that's f of 0 and f of 1. Oh, great. So we're adding f of 0 to f of 1, and f of 0, I believe, was 1, and f of 1 is a. And so if we're adding those, we're going to get a plus 1. That's nice. It's already looking quite good. Now the middles, this is where it gets a bit more abstract, isn't it? You're going to have f of 1 over m firstly, because that's your x coordinate there, so you're going to be plugging it in to find the y coordinate, plus f of, now what's this going to be? It's going to be, remember that, like, if that's 1 over n, I'm just writing down the gaps there, yeah? So if I write down the coordinates instead, well, the coordinates are going to be 1 over n, 2 over n, 3 over n, because that's going to be twice as far as that one, 3 over n, because that's 3 times as far, and so on and so forth. So this is actually 2 over m plus f of 3 over m plus, now this is obviously your nasty bit, isn't it? Now it's the bit just before f of 1, the last one. That'll be m minus 1 over m. And that's the last one, and that's the end of our trapezium rule. Now, obviously, this begs the question, right, I really need to deal with this f of 1 over m. Now, b equals f of 1 over m, so that's kind of good news. But what about 2 over n and 3 over m? Well, immediately you should be thinking up here, this is got to be handy for this, because, f of 2 over m is f of 1 over m plus 1 over m. And I'm writing it like that so I can apply this rule and say, well, that's the same as f of 1 over n times f of 1 over n, which is b squared. Because remember, f of 1 over n is b. And you can make exactly the same argument. I'm sure you're going to see it's not going to look any different. You're going to have 3 1 over n's here. Then you have them all times together, and you're going to get a b cubed for f of 3 over n, and so on and so forth. And so in general, f of k over n is equal to b to the power of k, yeah, if you like. And so what have we got? Well, that makes things a lot nicer. Let's start plugging some stuff in. 1 over 2m. F of 0, I think, was 1, and f of 1 is a. So you're going to get a plus 1. I think I'm just going to check that. I'm pretty sure that's it. I keep getting distracted by this. That's a minus 1, but that was when we subtracted them. That's a different answer. So yeah, a is f of 1, 1 is f of 0, so I'm adding them together, and then 2 times, and then they do this all the time. They love doing this. This is b squared, this is b cubed. As soon as you get on these papers a geometric or arithmetic progression, recognize it and use that formula. So this is actually going to be b to the n minus 1, that last term. Like I say, that's k basically. And what have we got then here? Well, let's just quickly do a little intermission and figure out the GP formula. So b plus b squared plus dot 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 b to the n minus 1. Well, that equals, well, what does that equal? We've got first term is b, common ratio is b. So we've got b times 1 minus b to the, now this is always the same power as that, over 1 minus b. Yeah, 1 minus r. So that's what we've got for that. Ooh, looks a bit ugly, but if we just multiply that b into there, straight away you should be thinking, let's get that back to b to the n, because this is the bit actually, I think this is the bit where I definitely didn't immediately see it. Okay, if we've got b is f of 1 over n, then of course b to the n is f of 1 over n times f of 1 over n times. It's it's such a nice result, this. If I can just show you up here. We just need to use our formula again, our trusty formula of b to the n. Well, that is f of n over m, which is f of 1. Of course it is, which is a. Right. Once you figure that out, you've got this question. You really have. So this is actually b minus a over 1 minus b. Cool. Right, let's just go back to here. We'll plug that in, and everything will hopefully tidy up nicely. 1 over 2n, a plus 1 plus 2b minus a over 1 minus b. Naturally, we want a common denominator there. That's going to be a plus 1, 1 minus b, plus 2b minus 2a, all over 1 minus b. And then we'll just tidy that. And because we know the answer, it kind of gives us an advantage. But you're going to get an a minus a 2a, so you're going to get a minus a here. You're going to get a plus 1. You're going to get a minus ab. And then you're going to get a minus b, but plus 2b. So that's a b. over 1 minus b. And let's just have a look at the answer, because I think the answer is, yeah, b plus 1 over times a minus 1. Now, I bet you that factorizes to b plus 1, a minus 1, hopefully, if we haven't made a mistake. Let's have a look. B plus 1, a minus 1. So let's just write it down and look at it. This is what I like to do in optimistic hope. Yes, sure enough, if we times this out, we get BA. Oh, have I got? Oh, yeah, yeah. But hang on, I think I've got my. I think they've got their B the other way around. Yeah. So if I think it's the negative of this. Yeah. Because if you notice, just ignore that negative. I'm going to get all the signs the wrong way round. Now, B times A is BA, but once you get to the negative, you get minus AB. You get an A, but oh, it's minus A. You get a minus 1, oh, but it's a 1, and you get a minus B, but it's a positive B because of the sign. But of course, I've got my bottom the other way around to them. They say B minus 1, and I've got 1 minus B here. So that works nicely. I'll just apply the negative on the bottom, and I'll get exactly their result. So 1 plus B, A minus 1 over B minus 1. And it's proved. That was, probably the nastiest bit of question. The next bit is not that bad at all, really. I don't think so anyway. I don't think it's too bad. Let's see. So we've got in, yeah, and we've got I. Let's go back to what they are. So there's in, and there's I is just a minus 1. So let's just start from that principle. So a, well, let's write it the other way around. 1 over 2n, b plus 1, b minus 1, a minus 1. That has got to be greater than or equal to a minus 1. Now, looking at this, okay, first things which stressing me out is they've introduced a power here. Yeah, that's kind of stressing me out. But I tell you what I am liking about the look of this is that a minus 1 cancels nicely, and 2n I can multiply over. So I've got b plus 1 over b minus 1 is greater than or equal to 2n. Looks a bit tidier now. Now, immediately I'm thinking I don't like the B's. Yeah, the B's need to go. But I should be looking where I'm going. And remember, I can get rid of the B's because we've already decided that B to the N is A. Yeah? Do you remember that result? That was the crucial result here. It was, when you realize that in this question, it really does help you massively. Okay, so we're going to obviously trade B for A like that, and obviously as we've got B's and not that, we're going to have it as a to the 1 over n. So I'm going to have it as a to the 1 over m plus 1, a to the 1 over m minus 1 is greater than or equal to 2n. At least I've got the right letters in there now. They've got n's and a's, I've got n's and a's. It's looking much more positive now, isn't it, really? Always, let that guide you, sort of like algebra. Are you making it look more like the answer? Okay, so now if you look, they wanted to produce a 1, yeah? And this is an old trick. Like, you want to look for this when you've got a 1 plus a fraction. Like, well, and sorry, I'm not helping you here, but yeah, okay, when you've got 1 plus a fraction, why don't we write this as a to the 1 over n minus 1 plus 2 over a to the 1 over n minus 1, yeah? Because obviously that's the same as the line above it. Why have you done that? Well, it's because now I can do that divided by that is 1, and then plus 2 over a to the 1 over m minus 1, yeah? It just seems like that might be the way to go here. And now all I've got to do really is just isolate my a variable, the value of a. If I take a and make that the subject, then surely this will be all right, hopefully. It's starting to look a little bit more like their one. Look, I'm going to get a 2m minus 1 here, and it's just looking nice, isn't it? Maybe it's not that obvious, but it's looking nice now. So 2 over a to the 1 over m minus 1 is going to equal to 2n minus 1. And then let's, now you've got to be slightly careful here, but because a is positive, we can actually safely sort of like rearrange this to turn it into what they've got, which is 2 over 2 to the n minus 1. Let me just show you, sorry. they've got 2 over that. So I obviously want to multiply that over there and take that underneath. So I've got that there and I've isolated it. And then I'm really, really, really close to the answer. Just ask yourself, can you do that? Well, yeah, you can do that because I believe they said, did I mention A is positive? Well, f of x is greater than or equal to 0, and this is an f of value, so clearly this A is positive. Yeah, so we haven't got to worry about that being, negative. Oh, I suppose it could be -1. Well, is it greater than 1 as well? Oh, A is f of 1. So, I mean, I actually know that, once again, A is E, isn't it, here? Like, because we're talking about the function e to the x. So, so it's kind of amusing, really. But the fact is, you can multiply it across, and you get 2 over 2m minus 1 is greater than or equal to a to the 1 over m minus 1. Add the 1 over, do to the power of, and you've got their answer, that a is less than or equal to 1 plus 2 over 2m minus 1 to the power of m. Yeah, I'm just trying to just more strongly justify the fact that a cannot be, a to the 1 over m minus 1 can't be negative. Maybe what there's going to be an obvious result here. Well, since f of x is bigger than 0 and the integral from 0 to 1 equals a minus 1, this must be positive because it's a positive area because the curve lies above the x-axis. There you go. That will do. That's I'm happy with that justification. I just wanted to properly explain that because, why should you be able to time something across an inequality if you're not sure if it's negative? You've got to be careful with that. You've got to be really careful. Okay, hope you enjoyed the video. That was pretty much the whole thing. Cute question. It really is. It's quite nice. It's good in some ways. It has the classic geometric progression in it. They love doing that. But yeah, hope you enjoyed it and keep up the good work. Bye bye.